Perfect.
Full screen, so perfectly.
Perfect. Then we can start. So hello everyone, my name is Celenk, and today I'm going to present you our work on machine learning based KPI monitoring of video streaming traffic for the quality of experience estimation. So this is a joint work with Professor Thomas Bauschert and Markus Eckert from Technical University of Chemnitz. And I would like to start with a short outline. First, I'm going to talk about our motivation for this research, and then I'm going to introduce you to our methodology and how we collected our data and how does our test setup looks like, and talk about also what traffic scenarios we have used for collecting the data and how we pre-processed our data for preparing it for machine learning, and also going to briefly talk about my statistical features that we used for this model. Also briefly explain how we handled our class imbalances in our data set. Then I'm going to present some of our results and then conclude my presentation with what could we do in the future. So let's begin with what motivated us for this research. As also Nicolas briefly mentioned in his presentation, assessing the videos, assessing the QoE is challenging, especially for the video streaming, due to the increased usage of encryption, and the video streaming is having a really big share in the global IP traffic right now. So this is a big problem that needs to be solved. And one alternative to the traditional solutions is the machine learning approach, which has been gaining more interest in the research community in the recent years. And this is also what we focus on our research, but we try to detect the key video events such as playing, buffering, or quality changes as the video is still running, so in real time and when the data is on the fly. And this brings another challenge, which we will talk about today. I would like to first start with the methodology with our workflow. We have basically designed a Python-based machine learning pipeline, which consists of 4 main modules. And the first module is the data collector module. It basically monitors the traffic all the time, and every second it creates a pcap file with the traffic traces, and as soon as there's a new pcap file, the statistics collector and the preprocessor are responsible for extracting the useful statistical features from the encrypted raw data and preparing this data to the machine learning stage. And what the machine learning based predictor module does is that it has a previously offline trained machine learning model deployed inside, and it makes predictions every second, whether the video is currently buffering or if it's playing or if there are some quality changes. And this is basically the overview of the pipeline and how the workflow is. And now I would like to talk a little bit of how we collected our training data and how our testbed looks like. Basically, I have collected the data in a home network with 2 Android smartphones and a computer that is set up as a bridge network. It has the TC tool, traffic control tool in it for traffic emulation, so that we can emulate some bad traffic scenarios. And what the smartphones have is a QTS app, which is a customly designed app by one of our project partners for the automation of the data collection. Basically, what it does is it constantly plays YouTube videos, the selected YouTube videos, and at the end of each session, it creates a CSV file with the key video events that we are interested in and their timestamps, so that we know exactly at what second which video event is happening. And this is what we use to establish our ground truth. And here are the traffic scenarios that we have used while collecting the data for emulation. And as you can see, we have 6 scenarios. In the first scenario, we didn't make any manipulation. We left it as it is. And then we introduced some bandwidth limits, some packet delays, also packet loss, and packet corruption. And there's also in the 6th scenario larger packet loss to trigger more buffering events or quality changes. And here, after collecting data, we have to pre-process this to train our model. Before training our model, and as I mentioned, we have basically 2 sources of data here. One is the traffic traces, which are in the duration of 1 second each. And we have the video events from the QTS app generated after each session of video. And we have basically from the PCAPs, we have calculated the packet statistics, which I will mention in my next slide. And also we have extracted the timestamps. And also from the CSV file, we extract the timestamps, and we also extract, of course, the key events. And this is what we use to label our data. By matching the timestamps of both the PCAPs and the events, we basically merge this into a data point. And what we also use is the data that was observed in the previous second. So we combine these two as well, because we thought that it could be helpful for us especially for the quality that changes, to know what was happening also in the previous second. And this is basically how we create one single data point in our data set. And of course, we repeat this for every file that we have. And I would move on with the statistical features that we have used. As I mentioned, they're packet-based statistical features, and they're computed in bidirectional way, so both for uplink and for downlink each. What we were interested in were the total and average number of packets, and also the packet sizes as well, like total, average, maximum, and minimum, and inter-arrival times of the packets. Again, the total, average, maximum, and minimum. And these can be really useful because you can observe this for the data on the fly. So these can be computed quite fast. And this was the biggest challenge that we currently had, that the data set was highly imbalanced because of the YouTube's adaptation algorithms, that it tries not to have many buffering events or quality changes for the user experience. But we used, of course, even when we used traffic emulation, it wasn't so much possible to have a very balanced data set. As you can see, in the first column, we have many playing examples, but not so many of the other classes. So what we did is we basically oversampled our data using the SMOTE technique, which is synthetic minority oversampling. What it does is it picks examples from the minority classes, and it synthesizes new examples that look exactly like those by checking the neighboring data points. And at the end, after the SMOTE, we have a balanced data set that has the same number of examples from each class. And then we can talk about the model training we have done offline. We have tried different algorithms such as decision trees, k nearest neighbors, and also random forest. And we moved on with the random forest because it was yielding the highest accuracy. And we basically separated 80% of our training data for training, and 20% for testing. And we also use tenfold cross-validation because we have limited data and we want to make the most use of it. And then I would like to present some offline results first, which is done by the test set, which was the 20% of the initial data. As we can see, we have a testing accuracy of 88%, which is pretty good, but when we look a little bit more in detail to precision, recall, and F1 scores, we see that there's a problematic class, which is the quality downgrades. We see that these values are quite low, and it might be a big problem for the online case when the model is deployed for classifying unseen examples. So this is something that we are currently looking into for improving it. But the other classes seem pretty okay. So we have basically some preliminary results for the online testing where we have deployed a simplified version of our model, which is only looking at buffering and playing examples. So only looking at whether the video is playing or buffering. And here I would like to present 5 example test cases to show how the model is performing inside the pipeline online. So we see that when we have a look at the left-hand side, we have the real events. And on the right-hand side, we have the predicted events, which are the predictions of the model. And for example, in the test number 3, we have the model has caught almost all of the buffering events. It's quite close to what was happening in real, and but also in the fourth example, it is quite well. But also for example, in the first and second test runs, it wasn't performing so well. It only caught half of the actual buffering events. And on the fifth one, it was also interesting that it actually guessed more buffering events than actual number. So when we looked into it, we saw that the model starts to perform less accurately when the network conditions gets bad. And this is a problem which shouldn't be there. And this is what we are currently examining. And this brings me to the conclusion and what could be in the future. So as a conclusion, it is possible to predict such key video events on the fly using the machine learning technique, especially with such a pipeline. But the dependency between the network conditions and the online performance is something that we still have to solve. And we have worked, it is still at an early, it's a work that is still at an early stage. So we only worked with a small data set, and we need more data to improve our model. And this will also improve the online accuracy, hopefully. And in the future, we of course would like to train and test with more data, and also not just with YouTube, but other streaming services such as Netflix or others. And we also will improve a little bit on the future engineering so that maybe we can drive different statistical features than only packet-based. And we actually want to adapt a continual learning strategy so that while the new data is coming, we can use this new data to retrain the model and automate it somehow. And I think this would be really helpful for constantly improving our model. This brings me to the end of my presentation, and I'd be happy to answer any questions if you have. Thanks for listening.
Thanks, Olga. So, questions? Danilo, you can open your mic and ask.
Okay, so hello, and thanks again for your presentation. It was very interesting. Actually, I work a bit on this kind of scenario, in this kind of problem. So I was wondering, when you define your traffic scenarios, how did you pick the metrics, for instance, the reference where you did no manipulation, the bandwidth limitation, and so on? Did you choose these 5 scenarios in somehow?
It was more like trial and error, and we have also noticed that we should actually try more scenarios, maybe even worse scenarios than we currently have. This could also help with getting more buffering and quality change examples. But currently, or in the first version, it was trial and error. So
Okay.
we just thought, okay, this should be enough bandwidth limitation to trigger some buffering events, and we used it that way, and we just kept switching between these scenarios.
Oh, okay. I share with you a link. This is a work we did about traffic shaping that might be helpful for you. I don't know if it could help or not, but
I
does
would
some
love to see
kind of traffic shaping related to mobile networks. So basically, it helps you on understanding these traffic scenarios.
This is
So try
perfect.
defining a kind of traffic scenario based on real data. This is why I was wondering if these constraints were based on some kind of pre-knowledge, so that you emulated like a network usually overloaded or something like that, or if it was kind of trial and error. And
Yeah. So I
in
will
this case, I
definitely.
think it could be useful.
Yeah,
If
I will
you
definitely have a look.
Okay, that's it.
Thank you so
Thanks
much.
for your presentation.
Thank you as well.
Other questions? So just about curiosity, at the end when you were talking about the future work, so you say training and testing with more data and other streaming services. Like, I didn't get, do you mean to have a single model for each streaming service, or a single model that is able to cope with the different streaming services, and also maybe so will apply in general to new streaming services without the need to retrain it?
Yeah, it's an interesting question, actually. Ideally, I would like to have a model that is able to cope with all sorts of streaming services, but in reality, especially for a real-time system, it might not be so possible. So maybe we would have models one model for each service that should also be realizable. So I think this is something that we have to experiment a little bit.
Okay, we'll see in the next paper. So thanks, Ozjan. And so I guess that now we can move to session 3, but